Assalamu alaikum. Thank you very much for giving me the opportunity to present my research idea here on this prestigious platform. So today I'm going to talk about using plastic waste for water treatment. And my name is Umer, and I'm from Government College University, Lahore. I'm assistant professor there, and I'm studying uh, mainly environmental remediation, environmental monitoring, risk assessment, and circular economy-based methods for the treatment of water and soil, for the removal of pollutants from different environmental compartments. And before I go into discussion on how we can use plastic waste for water treatment, I would like to share an experience that I had during my PhD when I was determining the concentrations of perfluoroalkyl acids. It's a group of emerging pollutants. Um, so I was studying their concentrations in River Saale in Germany, and I found out that the concentration of perfluorobutane sulfonate, which is actually an alternative to perfluorooctane sulfonate, after it was banned by in the Stockholm Convention 15 years ago. So perfluorobutane sulfonate was determined on different locations, and we found out that the concentration of perfluorobutane sulfonate has increased downstreams from 5 nanograms per liter to almost 10 nanograms per liter. So we had a hypothesis that there should be a point source on its way. So when we were investigating it, we found out that there was a treatment plant. uh, the effluent of this treatment plant was not able to remove it. Rather, it was pre-concentrating it and releasing it in the effluent in the surface water. So this indicates the inefficiency of treatment units, especially when we are trying to uh, um, you know, remove emerging pollutants, because emerging pollutants are not very well understood, and we do not know much about their properties, about their characteristics, which we can utilize to remove them from water. So, after I came back to Pakistan, I decided to think about methods which can be used to remove these pollutants. And one of the option was to use some waste materials and convert them into materials that can be used for water treatment. So one idea was to convert plastic waste into membrane and then control the properties of that membrane to remove these emerging pollutants. So why plastic waste? Because Pakistan is one of the countries where the recycling rate is very poor, almost 18 to 25%, and that is also usually through informal sectors. We have single-use bags, PET bottles, packagings, disposable food packagings, and so many things. So the plastic is a huge waste in Pakistan, and usually it is calculated to be around 15 to 20 kilograms waste per person per year. So that is, let's say, equal to almost 4 million tons per year. So that's a lot of plastic, and that is in the environment, and we all know that plastic is a mess. It can really create issues in the waste management, and it's it's not degradable easily. So yeah, so the plastic is a huge thing for the environment. So I thought how we could use plastic waste to convert it into filtration membranes, because virgin plastic is a resource. But if we could use the waste and recycle it, this could be a very good thing, because then we would not be dependent on a new virgin plastic, and we would also be removing plastic from the environment and upcycling it to a better um, product. So I found out that there are various ways to do that, to convert plastic into a membrane, and one is a chemical way, let's say, and the other one is a mechanical way. So there is an electrospinning technique, a very famous thing usually chemical engineers utilize. But I was a chemist, so I wanted to do something with more with solvents and chemicals. So there was a method which is called NIPS, or non-solvent induced phase separation process, that can be used to convert plastic into a membrane, and then we can also control the properties of that membrane, um, which can make it specific plastic membrane for a specific pollutant, let's say. So the process is to make a solution or a casting solution in some solvent. So now that we need to cast it in the form of a membrane. We can control the thickness during that phase, and then we can uh, do liquid-induced phase separation by putting it into a non-solvent bath. Let's say I have a solution of PET plastic and let's say phenol, and then I would cast it in a non-solvent bath, let's say in water or water and ethanol. The other way is to remove the solvent through whips or vapor-induced phase separation, where the solvent is evaporated and leaving behind the membrane. And the third is TIPS, or let's say temperature-induced phase separation, where the cast is put in a cool coagulation bath, where a sudden change in temperature would separate the membrane. And when we are making a casting solution, we can add additives to control the properties of that membrane. For example, we can make it an anti-fouling membrane and so on. So, for example, if we have a PET membrane, we can, so we want to make a PET membrane, we can use waste plastic bottles. We can cut them into small pieces and dissolve them. And there are different types of solvents mentioned in literature that we can use. For example, trifluoroacetic acid or dichloromethane or trifluoroacetic acid alone, phenol, and others. Then we can cast it, and then we immerse it in a phase. So non-solvent induced phase separation. Let's say we can put it in water or in methanol or in a mixture of water and methanol, and the membrane is separated and it is washed, and then we have a porous membrane that we can use for water filtration. We can also do that with polythene bags, so we can dissolve it into, let's say, xylene or some other suitable solvent. Then we can make a membrane and put it in a water bath, and then the non-solvent induced phase separation takes place, and we have uh, a polythene membrane. This is a study done by a group. So I am using this slide to indicate how the conditions can control the filtration, let's say, process, or also can control the water permeance. So for example, I have highlighted three points. If you look at it, so we have, let's say, 16% PAT. So we have 86 liters per hour per meter square per bar water permeance. with almost 26% NaCl reaction. So that is like desalination process. But we can increase the pore size, for example. So we can add polyethylene glycol, let's say, and the pore size is increased, and let's say now the permeation has increased to 109 liters per hour, but the rejection has reduced because the pore size has increased. And similarly, we can use DCM as a co-solvent, and we have yeah, better rejection and low permeance. So this is like very common to know, to understand that, it's easy to understand that if we have bigger pores, we have poor rejection, more permeance, but if we have smaller pores, we will have lower permeance, lower flow rate, but we will have better rejection. But then we would also need maybe more pressure um, to pass it through the membrane. So these are the membranes which we made in my laboratory. So we have, so you see, we have two different kinds of membranes, and this is actually a same material polythene membrane, but under different conditions. So you can see on the left side, the membrane is not very well made because of the conditions we use for making the membrane. And then we have xylene at a little higher temperature. Then we made a cast, and then we put it in water, and then we have a better membrane. So you can see that you can change the temperature during so dissolving the plastic, and you can use additives, and then you can control the structure and features of that membrane. So this is an interesting work, and there are some examples from literature where the people are using plastic waste plastic based membranes. For example, PET based membranes have been used for the removal of humic acid or chromium, or even for gases for the separation of methane and carbon dioxide. So this is possible. However, there are some pros and cons, obviously, and yeah, so things still needs to be better understood, and further research is required to make it really happening that we can use waste plastic for water treatment membranes. And so this research is has a good correlation with the Sustainable Development Goals or circular economy. So, for example, we have we can use plastic waste to make membranes, which is an environmental beneficial strategy, and it is in line with circular economy. It is so it correlates with Sustainable Development Goal 6. That is about the sustainable management of water and sanitation for all, and also for the Sustainable Development Goal 12, which aims to significantly reduce waste generation or recycling or upcycling and reuse. So thank you very much. If there are any questions, I would be really glad to discuss about it. You can send me an email, or all you can contact me through this conference forum, and I'll be really glad to answer and discuss how this can happen and how we can collaborate. So once again, thank you very much for your time and for your patience. It was really good to present my work here. Thank you.